All right, we are going to go ahead and get started with linear equations. And today we're talking about linear equations from tables. So you may have seen, along your math journey, people making tables and kind of wondering how does that relate to an equation. So let's take a look. Our example is going to be Owen, Patrick, and Dia today, and they are running. So you can pause this video if you'd like to write down this table, but we're going to start with Owen. And we've got two things represented here. We've got the distance that Owen runs in miles. So we're going to write that distance in miles. And we also have his time in minutes. Those are our two variables. And hopefully you can tell that distance in this case is the independent variable and time is the dependent variable because the time it takes is going to be dependent on how far he runs. The other thing you have to understand about this is that he can't change speeds. So for this example, he's running at the same pace for the entire time. And yeah, let's see, is it fast or slow? How can we represent that with an equation that looks like y equals mx plus b? We're going to assume that there's a linear relationship here. We want to know what the pattern is. How do we use the table to determine that? Well, let's take a look. We know in our y equals mx plus b, we need a slope and we need a y-intercept. All right, those are the two things that are going to define this line, and we can get all of that from this table. I want you to notice that these lists here of distance and time are actually points. So we could write them as points like this. 0, 0, that's the first point. 1, 6, 2, 12. So they get paired up. 3, 18, and 4, 24. Now, do you remember the y-intercept is the place on the graph, right? The y-intercept is the place on the graph where it crosses this line right here, right? The b value. So if it crosses here, it's like 0 comma b. This value goes over here in the equation for b. So in this graph, we're kind of wondering, in this table, I should say, where is the graph crossing the y-axis? The graph crosses the y-axis when the d value is 0. And you should notice that that's happening right here. The d value is 0, and when the d value is 0, the t value is 0. So we could, without any other information, we could tell ourselves the y-intercept and put a 0 here. The 0 is the y-intercept because when he's run 0 miles, his time clocks in at 0 on his stopwatch. So the only thing that we need to find from this graph that we don't have is the slope. And it's actually really easy to find. So how are we going to find slope? Let's see, let's change the color and kind of make this green. We're looking for slope, the m value. Do you remember that the m value for a line, the slope, m just means the slope. It's the change in y values compared with the change in x values. That's what it's saying. Okay, it's not necessarily comparing these two things. It's not comparing the 6 to the 1 and the 12 to the 2. Instead, it's comparing like the 1 to the 2 as we compare the 6 to the 12, and then we keep doing that. We could do that, multiple times, and it would be the same comparison every time in the end. So this is kind of what we're looking at. As we go down this distance column, what's happening? We can see, hopefully, that you're adding 1 each time. Kind of squeezing this in here, but you're adding 1 each time. That is what's happening as you go from point to point. That is the change in x. That's what we're looking at. The change in x is really simple here. It's just plus 1. That is distance, the change in distance So you're not comparing, you're not subtracting a distance with, a time at this point. You're just looking at the distances, and you can see every time we move along this column, we go up by 1. Okay? Over here, hopefully you can see that we're going up by how many each time? Looks like we're going up by 6 each time. And it doesn't change. It's going up by 6 each time. And the reason is because his speed is constant, right? And so his change in y, or his change in time, right, is going to be 6 minutes. So this is a plus 6. We didn't even really have to subtract anything. Like in the past, we took 2 sets of points and we did our little formula. But in this case, we can just look by inspection. We can see that the slope is 6 over 1. Just write it as 6 over 1, which is the same as 6. So if we're rewriting the equation now, you could say, let's see, how do we want to do this? Well, we started y equals, we're putting in a slope here, 6x plus 0. So if we wanted to put it in y equals mx plus b form, the slope is 6. You could leave it as 6 over 1 if you wanted, but you get y equals 6x plus 0. Now, what else do you need to know? You need to know that we don't have to use y and x. We could switch those out with d and t because, t is the dependent variable. We're going to put that here. T equals 6 times distance, and then this plus 0 we don't have to write because plus 0 doesn't change the outcome whatsoever. So our final answer is just t is equal to 6d. So what does t equals 6d mean? It means for every mile that he runs, it's going to take him 6 minutes. So this is really t is equal to 6 minutes per mile, and then it ends up being times the number of miles, right? So that's in distance. So distance will cancel with distance like this. When you multiply those two things together, like this distance is in miles, it cancels with miles, and then you'll be left with a time. But it's not going to just be time. It's going to be whatever, right? It's not going to be just 6. It's going to be 6 times whatever the distance is. So for example, if he wants to run 10 miles, t is equal to 6 minutes per mile times 10. And we know that this is 10 miles. How long is that going to take? T is equal to 6 times 10 is 60. Miles cancels with miles because units can cancel if you multiply and divide as well. So we end up with 60 minutes in this particular case. So we could use this equation to kind of figure out how long it's going to take Owen to run certain distances because he has a time of 6 minutes per mile. I'm going to move on to Patrick. Let's take a look at Patrick's numbers. They're a little bit different. So we have distance and time for Patrick. Still means the same thing. D means distance. T means time. But Patrick's numbers look a little bit different. 0, 1, 2, 3, and 4. But then we get 5, 10.25, 15.50, 20.75, and 26. So what's going on here? Is Patrick fast? Is he slow? Who can say? But we know that these are points. We know that this is a 0.05, 1, 10.25, So you can go ahead and write all these. 15.50, 3, 20.75, is that right? And 426. These are all points here that represent Patrick's distance and his time. We could graph these points if we wanted to, but there's something interesting going on here. We've kind of said, okay, we could write it as y equals mx plus b. We could also write it as time is equal to the slope times the distance plus b. So we're kind of replacing x and y with t and d. But what's happening? The first thing we said when we want to calculate b is we just need to look at where the kind of independent variable is 0, and that would kind of determine where we cross the y-axis. So if we drew ourselves again a little graph, hopefully you can see that we go, when we're at 0 distance, our stopwatch says 5. Why is that? That doesn't make any sense. Well, it does make sense if you think about it in context. This could actually happen. It could be that Patrick started his stopwatch before he actually started running and he forgot about it, right? So maybe when he looks at his watch to start running, he already has 5 minutes on the clock. So that could happen. And that would mean that his y-intercept is not 0 because his time was running. And so when he hasn't run anything, his time is 5 minutes. All right, let's take a look and see how to rewrite that. Okay, so we're going to say t is equal to m times d plus, and we're going to put in 5. Our 5 minutes goes there because he starts at a 5-minute time. The next thing we need is this slope, and the way we're going to find it is we're going to compare how are these things changing as we move down compared to how these things are changing as we move down. All right, what's happening? Well, we can see hopefully that we're going up by 1 each time over here. Again, we've got a lot of information. And then what are we going up by each time on the stopwatch? It looks like we're going up by 5.25. If you wanted to confirm, you could take the 10.25 and subtract the 5. So the difference between those is kind of the change. But it has to be the same each time if we're linear. The 5.25, right, is going to show up. So what does that mean? It means that we know that our slope is change in y over change in x. That is our slope. And we're saying that that's going to equal our change in y variables is our time, our change in time, over our change in distance. And we end up getting this 5.25 for every 1 mile, right? That's your slope right there. So how can we rewrite this? We can put this as t equals 5.25. We don't have to write the 1 if we don't want to. 5.25d plus 5. So this is telling us that even though Patrick is forgetful, he's fast because, there were 5 minutes on the clock to start with, but he's going to run a 5.25 minute mile, and that's pretty fast. And that's how you find that. All right, last but not least, let's check out Dia. We said that Dia is going to be running, and it's going to look a little different. Same thing, because we're kind of creating the same kind of scenarios, but with different people. So for Dia is going to run 0 miles, 0 minutes. But then Dia is forgetful in a different way. Dia only looks at her watch every 2 miles. How does that change things? Can we calculate how fast Dia runs or the pattern of her running if she doesn't clock at every mile? And the answer is yes. We're still saying D is distance. We're still saying T is time. And then we know we're trying to come up with an equation of y equals mx plus b. Or in this case, we're saying T equals m times d plus b, same as before. The y-intercept is the b value, the slope is the m value, and then we're replacing the y and the x with the t and the d. So don't forget that these are points over here, 0, 0, 2, 16, 432, and 648. And hopefully you can see, without even drawing a graph, that this is going to be the y-intercept, which we like. We like it if she hasn't run any, that her stopwatch says 0. That makes our lives easier, so we can rewrite this. T equals m times d plus, and we can put that 0 in there. Right? Her stopwatch is starting at 0. But what's happening here when you look at kind of the change going this from here to here, from here to here, what's going on here? And also, in the distance column, well, it's a little bit different from before because since she only clocks every 2 miles, this is going up by 2 miles every time. Right? 0 to 2, 2 to 4, 4 to 6, that's a change of 2. And then what about this time? Well, we're going up by 16 plus 16 plus another 16 plus another 16. Is she running 16-minute miles? Well, let's take a look. We know that the slope, we said, is the change in y over the change in x, which in this case is kind of the change in time over the change in distance. And look at what happens. Change in time is going up by 16 for each new recording, from 0 to 16, from 16 to 30. So it's changing by 16 each time. The distance is changing by 2 each time. So what you end up getting is 16 over 2, which can be reduced. 16 divided by 2 is 8, or 8 over 1. So Dia is not running 16-minute miles. Dia is running 8-minute miles because this is a unit rate. So when there's a 1 in the bottom, it's nice and easy to see what's happening with her pace. It's 8 minutes per 1 mile. And we like unit rates because they're easy to compare. So we end up getting something that looks like this. Instead of t equals md plus 0, we're going to write t is equal to 8 times distance plus 0. And we don't actually have to write that if we don't want to. So we could write t is equal to 8d and be happy with that. And that is a linear equation that represents how Dia, her running pattern. So we've got 3 different people, 3 different scenarios, and 3 different equations from tables.